So, good morning and welcome to the, sixth lecture in Lattice Boltzmann methods in the winter semester 2022-23. Everything audible? Okay, so no. Okay, so we are audible apparently. Not everybody here. Now I'm also starting the. Wait, just one moment. Okay, now we also have the recording. Anybody still coming? No. Okay, then welcome to this lecture on asymptotic analysis, in which we will cover a lot of ground. I have here some text that is more for your notes, so I'm not going to read through all of this. I just want to mention that what we're learning today, the asymptotic analysis, is really a key concept in understanding numerical methods in general and the Lattice Boltzmann method in particular. This is used for deriving the partial differential equations for a numerical method, for an existing numerical method, or for a method that is in development where we still have some unknown parameters. It is an algebraic method, so it is an algebraic method. It does not require any data. We don't do simulations and analyze the simulations. It's just we analyze the model itself. And the good thing is that this also works without any linearization, so it is applicable to nonlinear problems. And of course, it is not only applicable to the Lattice Boltzmann method, but today we learn it with the Lattice Boltzmann method. Okay, we have a challenge of the day, which is to take the D2Q9 Lattice BGK method and derive what equation it solves. So we are expecting that it solves the Navier-Stokes equation because it's designed this way, and we'll see whether this is true. So I've drawn here the velocity set for the D2Q9 lattice. So we use this now with two indices, I and j, where the indices I and j are from -1 to 1. And this leads us to the Lattice Boltzmann equation, which is the basis for our model. Lattice Boltzmann equation. So by Lattice Boltzmann equation, which I will denote as 6.1, by Lattice Boltzmann equation we mean this equation saying that the pre-collision state of f at the position x plus I, so this is the index, the x index, so it's I times the unit vector in x direction plus j times the unit vector in y direction times 1/2 a grid spacing. So we move 1/2 a grid spacing, and depending on t plus 1/2 a time step. So this is the pre-collision in 1/2 a time step and 1/2 a grid spacing away from our original point, minus, so we could put this on the other side of the equation, but here we like it to have everything on one side and everything together equal to 0. Yeah? So Fij, Fi minus Fij. So we turn a star, which is the post-collision term. So we turned the post-collision term into the pre-collision term. And the post-collision term was, of course, at the position 1/2 grid spacing backward. So it has, the post-collision state has moved 1/2 grid spacing, and it has processed 1/2 grid spacing in time. And this, all of this is 0, but we'll also call this now T, yeah, for later usage. So this is the post-collision state, the pre-collision state, and this is the post-collision state. So the post-collision state will move one full grid spacing and in one full time step, but in order to make the equation symmetric, yeah, we regard the post-collision state in -1/2 time step and the pre-collision state +1/2 time step. Yeah? So this is for simplifying the analysis in principle. Okay. So this is, yeah, right, we should probably say, so these are the unit vectors, so they have, they are all of length 1, okay? So now we want to do this for the BGK equation, which we now denote as 6.2, and the BGK equation looks like this. We have ij, so the BGK equation gives us the collision operator, so it specifies the connection between the post-collision state, yeah, which we now, for simplicity, write at the position x and the time t. The post-collision state minus the pre-collision state at the same time and space is equal to a relaxation frequency, and this into Fij equilibrium. So it depends on the equilibrium function, and it depends on the pre-collision state. So this is something we already derived in earlier in an earlier lecture. So we lost something on YouTube, I hope. This is just a mistake. Okay. So these are the two things which we have to combine in order to analyze. And now comes the first step, which is already useful in itself for the analysis. And some people just do this one, namely the Taylor expansion without asymptotic expansion. So Taylor expansion alone, but we need Taylor expansion anyway. Taylor expansion. Do a Taylor expansion of 6.1 at x and t, so at x and t as development points, right? Yeah, so we, so you see both in 6.1, both the pre and the post-collision state are not at x and t, but they are removed halfway up and halfway down, right? So we have to expand both of them. And because we put everything on one side, it is still 0, yeah, they still equal to 0, so 0 equals 2. Now we do the Taylor expansion at these positions, and of course in the two different, in all the different directions. So now this Taylor expansion has, of course, expansion parameters, where we have to, so we have 3 expansion parameters, one for the time that we call m, yeah, one for x, which we call n, and one for L, which we call, one for Y, which we call L, and they start from 0 and they go to infinity, obviously, yeah. So and now comes the usual Taylor expansion in 3 dimensions, which means we have 1 over m factorial, 1 over n factorial, and 1 over L factorial. And then comes the distance that we move. The distance that we move, so we are always moving in steps of delta x, right? So delta x, and this is both for x and for y. Then we move the distance, not the distance, delta x half. Yeah, so we move delta x half. We move delta t half by the power of m, and then we have its derivatives dt, m, dx, and dy. So this is the m's derivative of in t, the n's derivative in x, and the l's derivative in y. So, and now if you were careful and watching, you notice that there is something that I've been missing something, because we are actually not moving delta x, but we are moving I delta x or j delta x, right? Right? So, and this I will take, this I and j, I will take now to the f's, because for the f, the pre-collision state, we move in positive direction. So what we have here is I by the power of n. Remember, I is in the direction of x, right? And j by the power of L, yeah, which is in the direction of y. So, and both are positive because they belong to the pre-collision state Fij, and I don't write the indices, but this is now at the position x and t. Yeah, so we have to save some space, so I don't write these this index here. So that's relatively simple. Then comes a minus in the. Maybe I move it a little bit down here so that we see here's this minus, right? And minus the Fij post-collision, but now both space and time go in negative direction, right? And this, they are coming with these, again, with these powers, so we have to now take this into account. They come with minus I, yeah, and I goes now to the power of n, minus j, which goes by the power of L, and what we must not forget is that there's also the thing in t, yeah, so that comes without I or j is just minus 1 by the power of m, and this goes into Fij asterisk. Okay, so now you see it's getting more and more complex, and this is going to increase now. There are 2 recordings of this lecture in YouTube already, and I have to admit that neither of them is completely correct. So I always make some mistakes. So it's your turn to keep me from making mistakes here, so that we finally have a correct recording of everything here. Hopefully. Otherwise, if something looks a bit fishy, then you could, then there's always the possibility that I made a mistake. Yeah. Okay. Now this is the expansion in F. What we now do next is we want to have an equation actually in the moments, because the Navier-Stokes equation where we are looking for is an equation, of course, in moments. And for this, we now introduce again the countable moments. By the way, my computer is stuck. Let me see whether I can somehow. do something against this. Sometimes it works to use another okay, yeah. So raw countable moments. So they are defined as already in a previous lecture as MAB being equal to the sum over I and j equal to -1 to 1. So this is over all the different directions. Fij I by the power of A and j by the power of B. And also we have this for the post-collision moment, which simply is the same thing, just with the post-collision distribution. So Fij post-collision, I by the power of A and j by the power of B. And then we have another form of this, which we call MAB bar, which is defined as the sum over I and j equal to -1 to 1. And now this is the average of the two. And if you remember the last lecture, if you joined it, then you know that this is the actual distribution. So the sum of pre and post collision, this is the actual distribution for which we solve the Boltzmann equation. We don't solve the Boltzmann equation for the pre or the post collision state, but we solve it for the average between the pre and the post collision state. Yeah, so and this goes into I by the power of A and j by the power of B. So, last definition for now is we also need to have this, what we call the collision operator, we denote by omega AB, being equal as now the, let me see whether the other one works again. Always have to do this switching, I don't know. So it's again is the sum over I and j equal from -1 to 1. So it's F, so because we now have the sum of the distributions, we also have to distinguish the difference, yeah? So we call this the collision operator because, so somebody has complained that I call this an operator because they say it's not an operator, it's just the effect of an operator. Yeah, but what the collision does is it turns the pre-collision into a post-collision. Yeah. So then the difference between the post-collision and the pre-collision, this is the collision. Okay. Yeah.
Where is the relaxation time?
There's no relaxation time in this because we do not specify how collision works. Yeah? We just say that what collision is the outcome minus what comes out minus what is going in. It's completely irrelevant at this point. How this is implemented, whether this is with relaxation or otherwise. Yeah? Okay. Now we kind of need these definitions, and now we return to our equation. Okay, I kind of made a mistake here, so I have to update all my numbers I just recognized, because this is now going to be 6.3. 6.3 because we take this equation 6.3 and take moments of this equation. Of 6.3. So taking moment of this equation, which we still have. So I said before that this 0 we call this thing T, yeah, just to give it a name, even though we know that it is 0. So this T here, excuse me for going back, but this T here is the same T that we have here, okay? Because this is the same equation, it's just the Taylor expanded version, and because the Taylor expansion goes to infinity, it is, so to speak, complete. Of course, mathematicians will always ask at this point the question, is f a smooth function and can we Taylor expand it? Yeah, that's for sure. So this Taylor expansion idea actually comes from a mathematician. So I'm now confident that we can kind of use it. It is of course true that f is not necessarily a smooth function, and this could in principle go wrong, yeah, but it turns out that it is going right because we solve an partial differential equation, and this has at least smooth solution. Or okay, we don't know whether the Navier-Stokes equation has smooth solutions, but we make the assumption and we get a result, yeah. So I mean, if you want to be really if you want to be the Pope of mathematics, you could question everything here. Yeah? So this is a engineering technique. Yeah, it's not necessarily completely foolproof. Okay, so we take the moments of this. So what does this mean? We have 0 is equal to t. And now we can take moments. Of course, if we take moments of 0, this will be 0, right? But on the side of t, we take ij from -1 to t, to 1, and sum this over t, I, a, and j by the power of b. Yeah, so these are the moments of this equation, and this equation is 0. So we need this t in order to specify that these are now the moments. And this should be done for any given. So these a and b, they are just parameters here. For any given a and b. Okay, so what does this lead to? I need always more space. So 0 is now equal to this sum in the beginning over I, j equal to -1 to 1. And then we have, of course, our Taylor expansion again with m, n, and l equal to 0. And this goes to infinity. And now we have the usual stuff of the Taylor expansion, which are the factorials of these counters. We have delta x 1/2 by the power n and l, and we have delta t half by the power m. Then we have all the derivatives, dt, the derivative x n and y l. So, and now comes our distributions, f, I, j, where we already have I by the power of n, and now we multiply this by I times by the power of a. So this becomes I by the power of n plus a, right? And again, j by the power of, what was it, l plus b. Okay, and now comes the post-collision state, which is a little bit more complicated because here we have minus I by the power of n, and this we multiply by I by the power of a, right? So I have to write this again here. So it's I by the power of a, and this into minus j by the power of l times j by the power of b. And what you should not forget is that we still have the time the time guy which is 1 by the minus 1 by the power of then m. And this goes into Fij post-collision. Okay, so why are we doing this? We are doing this in order now to recognize that what we have here in these brackets are actually moments. So we can replace this here and this here by their respective moments, yeah, where we, of course we have to take into account that on especially on the in both cases we have to take into account that there are that there is this minus in between. Question.
But is the sum of the derivative equals the derivative of the sum?
Is the sum of the derivatives, this is what we are assuming. We are assuming, yeah, so if this is for whatever reason that would not be the case, then this would not work. But so we are assuming that these are exchangeable operations. We're also assuming that we can exchange the order of the derivatives. Yeah, so there are in some analysis methods there are problems with this. This is known from the Chapman-Enskog expansion, but this is a different beast here. So now, okay, unfortunately, on my notes I have the wrong numbers, so I hope I'm not killing this now. Okay, we introduce now another equation 6.3, where we replace these distributions now by their moments, which gives us then an equation for the moment. So again, everything equals to 0. Yeah? So and now we have only the sum anymore over m, n, l, and these start from 0 and go to infinity. Here we have the usual stuff, m factorial, n factorial, l factorial, delta x 1/2 n plus l, delta t 1/2 m, all the derivatives. And then comes the moments. Okay, and you see we have here pre and post collision with a minus in between, and this minus I by the power of n minus j by the power of l. This gives us alternating signs for even and odd orders of n and l, obviously. Yeah. So what we actually have is either the sum of pre and post collision, or we have the difference between pre and post collision. And we just introduced what this means. The sum of both is m bar, and the difference is omega. Okay. So now we distinguish this. Of course, this requires some. Some looking at it and rearrangement. So I'm just writing it down first. So of course, we are talking about countable moments. So we have I, n plus a. So what we end up with is here as the first index of the moment, a plus n. Yeah. So we're counting up, and the second one is b plus l. Right? So, and now this happens only in the guys that sum up. So they sum up if we have 1 minus, okay, let me write it down. 1 minus 1 by the power of n plus l plus m. Okay? So if you look very hard at these guys, and I hope I made it correctly this time. You see, if n plus l plus m, if they are of, say, okay, let's say they are even order. They are even order, then this will be 0. Yeah, so because if these guys here are all even order, yeah, so they will be positive, and there's a minus in between. So conversely, if one of them, or if the sum of them is odd order, there's a minus, and then they will add together, and then we have it twice, right? So that's what we want to have here. And for the other guy, it's of course the other way around. So the other guy is is omega, and I write it with minus omega here. A n plus 1, so this is the same now, b plus l. And this is more or less the opposite, so it's 1 plus minus 1 by the power of n plus l plus m. And, okay, so there is one difference between these two definitions. If you go a little bit back, the one m bar is, you know, the average between the two, and the other one is the difference between the two. So in the MAB bar, we divide by 2, and in omega AB, we do not divide by 2. This is why we have to divide by 2 down here. Okay? So they turn out here the opposite, and we have this yeah. Okay, so this means, what does it mean? This means that if n plus l plus m, if this is even, the m disappears, and we have the omega. And if m plus l plus m is odd, the omega disappears, and we have the m. That's the meaning between the two. Yeah. Okay, so now this is already useful in itself for analysis, but we can be a little bit more clever by doing one more step, namely the asymptotic expansion. So this was Taylor expansion. Now we come to what's the name of the lecture, namely the asymptotic expansion. So in the asymptotic expansion is in a smallness parameter, which we usually call epsilon, because we are more like physicists. So if you talk to a mathematician, they will usually call this thing h. And in both times, it is a generic smallness parameter. Yeah. Okay, I need a little bit text for our notes. So epsilon is a discretization specific smallness parameter. So the important thing is it's scalable. So it's something that you can change in your numerical method. And the thing that you could typically change in your numerical method would be the time step or the grid spacing. So these are the first things that come to mind, of course, depending on what your numerical problem is based on. It could also be something else, yeah? Okay, but it must be something that you can choose in your method, yeah? Not something that is fixed. So everybody listening to my lectures knows what is coming now. For everybody who's not now familiar with this, okay, some repetition. Any numerical approximation. So what is a numerical approximation? Or what do we understand by a numerical approximation? Completely generic, has nothing to do with Lattice Boltzmann in particular. We have a function phi of x and epsilon. So it has an independent variable x which could also be t, so could be space, time, whatever, right? And we have and it is also a function of a smallness parameter epsilon. And this phi x epsilon is some sort of approximation of a function f of x. So the function that we want to approximate should not be a function of our discretization parameter epsilon, obviously, right? So this is not a function of epsilon, yeah, and this is, so to speak, the truth. So what we have here, then this is the approximation. This is function approximated, the thing that we want to approximate. And it doesn't matter whether this is just interpolation or partial differential equation, yeah? So this is the guy that we want to approximate, but which we cannot solve. Yeah? We want to evaluate a function like the Navier-Stokes equation. We don't know whether the Navier-Stokes equation has solutions in the first place, so we replace it by lattice Boltzmann or by whatever. So what we have then is the truth plus an error. So in principle, you could always write it like this, truth plus error, but here specifically, we make the assumption that we can express the error in terms of series expansion in epsilon. So we have here a series in epsilon, a power series in epsilon, with the coefficients En, which are the error terms. So this is a series. It's not series. Okay, it's also series, but it's a series. Okay, expansion. It's a series expansion. So this we say in general, and now we say that numerical approximation or any method that we propose as a numerical method, then we call this consistent, and I also call this then correct. Yeah. So when is a numerical method correct? It's not correct when it has no errors. Numerical methods have errors. It is correct when it fulfills this criterion, namely that if the limit epsilon to 0, so when the smallness parameter goes to 0, then the approximation approaches the original function that was to be approximated. Then it is a correct method. Yeah. Okay, so this is the concept that we have to understand now. We have the numerical approximation that we call phi of x and epsilon. This is the so-called truth. So the truth is what f is producing plus is it a or in hierarchy? I know it's in hierarchy. In hierarchy. A hierarchy. I don't know. Yeah, this is a hierarchy of error terms. And they are separated, this is the important point that we are now using, they are separated by powers of epsilon. So, which means we can express our dependent variables, which in our case are the moments, MAB, say, MAB is now expressed as the sum from 0 to infinity, where epsilon n by the coefficients MAB of the order n. The same thing can be written for the collision operator and for post-collision moment, pre-collision moment, Barth moment. Yeah, just let me write this one guy here again. So this is n from 0 to infinity, epsilon by the power of n, and this AB power of n. Now, there is one extremely important thing now to keep in mind, even though it's obvious, but it is very important. Namely, these coefficients in the series expansion, they are not functions of epsilon. The thing is, all the dependence of epsilon we put in the series expansion. So the coefficients themselves, they are not functions of epsilon. So they would be the same for all resolutions that we use, okay? And just their weight would be different, yeah, depending on what epsilon we choose. Okay, so this was very general. What we do today is to look at the Lattice Boltzmann methods. And we are looking for the solution of the velocity field and the density field. So we make kind of a little bit use that we already know that we want to solve the Navier-Stokes equation, and we already know the variables that are solved in the Navier-Stokes equation. Otherwise, it would be difficult to first derive the variables that we are looking at. Yeah, but here we already know the variables. So they come as field parameters, field variables, and we look for them in the LBGK equation. So, which means we have a solution for rho. Rho being the density, the solution of the density from our BGK equation, and this is now composed of this hierarchy of terms, which we start at 0, rho 0 plus epsilon rho 1 plus epsilon square rho square plus and so on to infinity, right? So the rho itself is what comes out of our numerical solution, yeah, of our methods, and only one of them is the right result, and the other ones are error. Yeah, and we in a minute we come to what is the result and what is the error. So, and we have the velocity field, which we write as a vector u, and u again starts from u0 plus epsilon u1 plus epsilon square u square and so on to infinity. Yeah? Okay. Now we have been very abstract so far. Now the problem is, what is epsilon in the first place, right? Because we said it could be the grid spacing or it could be the time step. So is it the grid spacing or is it the time step? Huh? The problem being that in LBM has two numerically small parameters. And this actually is a problem because now we have choices, and the funny thing is once you have two, you have a vector space, and then you don't have two choices, you have infinitely many choices, because you can have any combinations of the x, right? So it's I will present you with just two choices, but the number of choices that we have in reality is infinite. Okay, there are different, of course, choices. Okay, choices for epsilon possible, but there are two which appear to be obvious in a sense. And these are the only ones that are really in use. And they have names. They come as the acoustic scaling and the diffusive scaling. And all of them have their fan club, by the way. And the discussions, which one is the more appropriate, it can become very emotionally. Usually it is this way that depending on what you are asking for, different choices are more appropriate. Yeah? So there's not one choice that gives you everything. Let's start with the one that is more popular, namely the acoustic scaling. And maybe it's also a little bit more obvious to use this. So acoustic scaling, let's say we think we're simple persons and we think, okay, let's say delta x should be proportional to epsilon and delta t just also should be proportional to epsilon. Yeah? So that would mean that obviously delta x by delta t would be constant. Yeah, but because when we make the one smaller, the other one goes smaller by the same amount. So what does this mean for the speed of sound? Speed of sound, Cs, is now in the lattice Boltzmann method. We now already assume, we have derived this in a little bit different context. We already assume this is 1 over square root 3. And delta x by delta t. So this is what we are usually using. We could also use something else, but anyway, this is constant. Yeah. So it does not physically change, which means that the speed of sound is invariant under scaling. So scaling always means that you change epsilon. And this is, of course, the reason for the name. And this makes absolutely sense if you look for acoustics. Yeah. So I mean, if you want to simulate anything in acoustics, you want the speed of sound to be physically fixed. Yeah, I mean, it could depend on the temperature, but it should not depend on your resolution. So that wouldn't make sense. So there's a clear application for this kind of scaling. Now, but it also has some problems. Okay, let's try to derive our problems. In the Navier-Stokes equation, we have two dimensionless parameters. Or you could say, wait a minute, in the Navier-Stokes equation? Okay, what we mean in the compressible Navier-Stokes equation. Yeah? Namely, we have the Mach number, which we only have in the compressible Navier-Stokes equation. So the Mach number, Mach, is equal to a physical velocity, I write u star for whatever reason, divided by the speed of sound. So u, this is a physical velocity scale. So if you ever wonder, I think this is for students sometimes not so obvious, so which velocity do we take? It does not matter, it's just a scale. It must be a somehow fixed velocity, okay? U star. So the next dimensionless thing we have is the Reynolds number. The Reynolds number. So for those from the previous lectures, in the Navier-Stokes equation, we do not have the Knudsen number, yeah, because the Navier-Stokes equation arrives from the Knudsen number in the limit of zero Knudsen number. Yeah, the Knudsen number has already been eliminated, in a sense. So you can recover the Knudsen number from Mach and Reynolds number, but they are hidden in this derivation already. So we have L. L is some physical length scale. Is some physical length scale, and then we have the viscosity, which in Lattice Boltzmann already derived this. It can also be derived by asymptotic analysis, but we already know that this is Cs square 1 over omega minus 1/2 into delta T. So that would be our viscosity. Okay? So now let us rewrite our Reynolds number. Remember, Reynolds number is something that specifies our problem. Can rewrite the Reynolds number by introducing this viscosity here. So we end up with Cs square 1 over omega minus 1/2 into delta T. So, and now into this we can substitute our Mach number, yeah, because we have here U divided by Cs, which is the Mach number. So we replace this by the Mach number. We end up with L, and now we have only Cs because one of the Cs is now in the Mach number, and this goes into 1 over omega minus 1/2 into delta T. Okay, now we are studying a physical problem, and studying a physical problem means, of course, that the Reynolds number must be independent of epsilon. Yeah, because the Reynolds number is the thing specifying dependent of epsilon. Yeah, the Reynolds number is the thing that specifies what we are simulating. Yeah, and epsilon is a parameter of our numerical method, so they should disappear. So now, if Mach and Cs are also scale independent, I love these indications of concentration during my lectures. Okay, so if they are also fixed, right? So we let us take them on the other side. Reynolds number times Cs divided by L star divided by Mach number, and this is now equal to 1 over omega minus 1/2 delta T. And this implies that 1 over omega, I write it this way because this is simpler, 1 over omega is L star M Mach number divided by Reynolds number Cs. So the important thing that all of this here is supposed to be scale invariant, right? Scale independent. And this now goes into 1 over delta T plus 1/2. So 1/2 is apparently scale invariant, but this here is scale dependent. So this depends on scale, which means that 1 over omega depends on scale. So, which we just derived is that in acoustic scaling, so meaning epsilon is proportional to delta t, omega is a function of the resolution. So, and the funny thing is, I mean, I don't know whether this is important now for the lecture, but if anybody of you ever tries to read papers on this topic, yeah, then you will find that this is more often ignored than it is actually taken into account in literature. Yeah, and I'm trying to fight against this for the last 15 years, talking to exactly the same people again and again and again, and they always agree on the spot, and next year they do it again. Yeah, so this is very often ignored. It's a very persistent problem, because it also makes the you know, if you ignore this, all the derivative, everything that comes later is so much easier. Yeah, so it's you know, you like to ignore this somehow. Yeah, so ignoring the dependence of omega on delta t, so which happens in acoustic scaling, because this is very popular to use acoustic scaling. Is, in my opinion, the most persistent error in literature in this regard. Is one of the, I cannot be very, you know, that this is the most important error in literature, in all of literature. I mean, in that field of literature. Yeah, don't overinterpret what I'm saying. Yes, please.
Maybe there are consequences on for this dependence on delta t in the analysis, but not in running the simulation. I mean, this is obvious when you run a simulation and you set your parameters correctly, no problem with that.
Yeah, but it has, of course, consequences for convergence of your method. So one of the problems is this is one of the problems why you actually don't have convergence of multiple relaxation time methods. Multiple relaxation time methods don't converge in acoustic scaling. Now you can ask that this may not be important in the actual simulation. So in the sense that you do not consider complete convergence because you are not running your time step to 0, right? But the thing is you are in some range where it works. So you are in a range in a time step where you make your time step smaller, you improve. And then when you make it smaller again, you diverge. So there is an optimal time step somewhere in between. Yeah, that gives you the best result. But in the idea behind all this error analysis is that the optimal time step for most accuracy is time step 0. And that would not be the case here, right? Okay, so next problem is that in acoustic scaling, the velocity is not asymptotically smaller it was not asymptotically small, I wanted to say, compared to the speeds, or to the lattice speed. Also to the speed of sound, because they would be proportional to the lattice speed. The lattice speed is equal to delta x by delta t. And this is constant. So what does asymptotically small actually mean? Yeah, so it's not asymptotically small means that when you make your crit smaller, then you get an infinite. Then also the difference between the speeds on the lattice, or the speeds, the speed in the lattice Boltzmann method, and the lattice speed would increase. Yeah, asymptotically small. So you have to distinguish between absolute small and asymptotically small. Yeah, because absolute small, you could say, okay, absolute small is something that is 10 by the power of minus 9, 10 by the power of minus 10. Asymptotically small is that when you make epsilon smaller, then the thing you are looking at is getting smaller too, right? And in this case, this difference is not getting smaller. So what we have here, whether your velocity is now 10 by the power of minus 2 or 10 by the power of minus 10, it would be fixed and it would not get smaller when you refine your crit. So if you have an error that depends on this speed, which you would have, then this error would not get smaller with higher resolution, and therefore you wouldn't have convergence. So this is again a question that you could ask, is this a practical question in the actual simulation? Because if you start from velocity 10 by the power of minus 10 in lattice units, yeah, then is probably your error is extremely small and you don't care, but you don't have convergence, because if you refine your crit, this error always stays the same. Yeah? So it will not converge. Yeah?
But what if I choose a sweet spot velocity for all refinements? Would this be?
No, usually not, because there are sweet spots where errors suddenly disappear, but they are always bound to special cases, so they would not be reproducible. But these things exist in fact. And it's a big problem that people believe in them and use them. Yeah? Because this is so unreproducible that it's kind of a gamble. Yeah? Okay, so all of this unfortunately leads to the condition that the lattice Boltzmann equation in fact cannot converge in acoustic scaling. So, of course, people force it to converge by making additional assumptions. So this is very common. So you could, for example, say, okay, we assume that our velocity is small anyway, and therefore we ignore all these remaining errors in velocity. And then, if we ignore this part of the error, then the rest converges. So this is possible, and this is actually usually what is done. Okay, now we look today at this scaling that allows us to get real convergence of the lattice BGK equation. And this is the diffusive scaling. Okay. So the challenge now is to keep omega independent of the discretization scale. So independent of epsilon. Okay, then return to our Reynolds number and say this was U star times L star divided by CS square 1 over omega minus 1/2 into delta t, and this is supposed to be constant. Yeah, very important. So now remember the CS square is some parameter theta, which we have already derived in a previous lecture, times delta x square divided by delta t square, and theta is the dimensionless temperature, which we already know is 1 over 3, but we ignored that we know it. So if this is so theta is dimensionless, so this is scale invariant anyway. So we have U star L star, we get here theta, and now delta x squared by delta t square into 1 over omega minus 1/2 into delta t. And this should now be constant for constant omega, and it would be constant for constant omega if we somehow can make these delta x and delta t disappear. And this is something that you can actually easily see, that omega would be constant if delta x square would be chosen proportional to delta t. Yeah? So then this guy would obviously disappear. Which now means that CS being the square root of theta into delta x and divided by delta t is then obviously theta, square root theta epsilon by epsilon square, meaning this is theta divided by epsilon, and this means that the limit of epsilon going to 0 of CS is infinity. And this implies that the simulated velocity is asymptotically small compared to the speed of sound, and by this also by the lattice speed. So what this means specifically is if you make your grid spacing smaller, you also make the lattice velocity smaller. Yeah? And therefore, errors in velocity will also at the same time get smaller. Now, of course, this guy has another problem, which of course is also the reason why it's not used in practice, often not used in practice. Namely, we have now eliminated the speed of sound. By this, we also have eliminated the Mach number, obviously, from our equation. And because this is now no longer scale invariant, and therefore, this is completely incorrect if we look at acoustics. So this way of thinking does not accept any acoustics. Yeah? Acoustics are gone. We are solving now the incompressible Navier-Stokes equation. Right, so, and what it means for the speed, which I just tried to indicate. Our physical speed is our lattice speed. Our lattice speed is dimensionless. Dimensionless into delta x divided by delta t. Okay? So which means that you, the guy that we see in the simulation, is the physical velocity times an epsilon. Yeah? So this is what I just said. You make epsilon smaller, you make the physical, you make the lattice Boltzmann velocity smaller, therefore errors in velocity will get smaller. And specifically this means for our result u, which we expanded as u0 plus u1 epsilon plus u square, epsilon square plus so on and so on, that this guy here is gone. Yeah? So we have no velocity zero term. Yeah? As we eliminated this, and our solution, the solution we are looking at, is not u, but it's u epsilon. So that would be the solution of our equation we are looking for, and all of this is error. Okay, so obviously if u0 would not be 0, this would also be an error, but then we didn't have a consistent method because this would be dominant. Yeah? So then our solution would be invisible within the noise, so to speak. Yeah? So the error must not be stronger than the solution. Yeah? Otherwise we don't have a method. Okay, so we are setting the stage here, right? Everything now was setting the stage to do actually our analysis. Yeah? Now let us go back to our asymptotic expansion of the LBGK equation, now in diffusive scaling. And we start this again, we go back to equation 6.4. Hopefully, because I lost here, I made a mistake with counting, so I just try to rearrange this and I hope this is correct. Okay, let's first return to this equation, so then it would be clear what equation I'm actually meaning. We have again the sum over m n l from 0 to infinity, and we have everything that belongs to the Taylor expansion, so all these factorials. We have delta t divided by 2, so I still write these guys here. dt m dx n dy l, and here is the countable moments in bar form, a plus n b plus l 1 minus 1 n plus L plus M, and minus omega A plus N B plus L. So again, this must be 1/2, and here is 1 plus now minus 1 by the power of N plus L plus M. Okay, so this is what previously came out. And now we write this as the equation 6.5 again with the asymptotic expansion. So we now use the asymptotic expansion on M and on the moments M and the collision operator omega, and so we start with 0, and we put all the epsilons that come out in one place. So we have the sum over M n L equal to 0, this going to infinity, and I do not want to write another sum, so I use now Q equal to 0. So Q is the order of the moments that I also have to count up. It's also starting from 0 and goes to infinity. So I now have 1 divided by M factorial, N factorial, L factorial. So now I take everything that comes with epsilon to the front, so that I have epsilon only in one place. Epsilon, so epsilon by the power of M square 2. Yeah, because it's already in the exponent, right? Yeah, so why 2M? Because we are in acoustic scaling, M is counting delta T. So we have 2 delta T in the exponent, right? We diffusive scaling, yeah. Did I say, okay, we are in diffusive scaling, so 2M, we have only 1 N and we have 1 L. And now we are also expanding the moments, so we also have Q, right? So now we put everything in this one place. Then here we have in this place up here, we also have this 1/2 by these guys. So I have to separate this out. 2 by the power of M. So here still. This has nothing to do with the scaling. This is why M is coming alone. Okay, and then we get the derivative in time with M, derivative in x with N, derivative in y with L, and here comes the expanded moments M A N and B plus L, and this is expanded in Q, again with 1 minus 1 N plus L plus M. Yeah, unfortunately these are big equations, so this is why we usually use computer algebra. You should join my computer algebra class where we learn how to automatize all of this. And here comes again 1 plus minus 1 N plus L plus M. So of course there's a lot of room for errors in this. Did I make an error?
The omega, that is Q.
The omega, right? So the omega is expanded in Q. Okay. So now this is a series expansion still, yeah, because it's a sum from 0 to infinity. So what we want to do is we want to turn the series expansion in a sequence of equations that we want to solve. And this is done in the following way. So this is, if you ever want to turn a series into a sequence, yeah, it's always done in the same way. You should actually know this. For the case you don't, I repeat it here from probably high school. So epsilon is arbitrary, but epsilon. So how comes that I write epsilon in mirror image? I'm really funny, right? So epsilon is arbitrary, but epsilon is larger than 0. Epsilon is a scaling parameter. We always want to solve the equation whatever epsilon, so it's arbitrary, but it cannot be 0, otherwise is everything gone, and it cannot be negative. Okay, it should not be negative. It also works with negative epsilon, but then in a mirror image. Yeah? Then timelines, everything goes backward. So, epsilon is larger than 0. What happens if epsilon is larger than 0? And we have this 6.5, this equation 6.5, we know this is equal to 0. Yeah? So this is 0 for, and it is 0 for all epsilon, right? And it would be 0 for all epsilon only if each order epsilon, say, okay, epsilon p is 0. Yeah? So, reminder from the high school, right? You have an equation a plus b epsilon plus c epsilon square is equal to 0, and epsilon is arbitrary, arbitrary, but it's not 0. Then this can only be 0 if A is equal to 0, B is equal to 0, and C is equal to 0, right? So that's clear. And this is called equating coefficients. Yes, and. No, all of them must be 0. So this means that we can, you know, there's a funny thing, I did not write it down.
Is it B or B epsilon equal to 0 and C epsilon square equal to 0?
So when epsilon, excuse me.
Is the term itself or the coefficient before epsilon that should equal to 0?
So the term in front of epsilon must be 0 in order for this to be 0 everywhere. So I just recognized that I did not have, since we are in this setting, I can actually take some overtime. I take the freedom of taking overtime because this is better than speeding up and making a lot of mistakes. So even though you want to go to lunch, I know, but anyway, it's so, you know, this is such an amazing message. You should be so happy now, right? Okay, we make, I've forgotten to write something down. I should write this equation down without epsilon. So this now, let's put it this way. We have this. Okay, I now I have to improvise a little bit. This Q. Let me see. The Q must be. Oh, why didn't I write this down? Let's see. So M by the power of n, so you have to help me with the improvising because you learned now everything. So we are looking, right, so we are looking at the case for a fixed, for any fixed order in epsilon. So this means that M, 2M plus N plus L plus Q is now fixed, right? So this means that Q must be any given order, say call this P. I call this P. P is then equal to 2. It's 2Q. Okay, now I made a mistake. It's not 2Q. Okay, so this, so we have an order P, right? So an order P of the equation, meaning that P being 2m plus n plus L plus Q. So then we can express Q as being P minus 2m plus minus n plus minus L, right? So this we call Q. Now I wrote this into my equation. I have to erase this P minus 2m minus n minus L. I'm going to erase this because this is in my equation now. And here we have eliminated all the epsilons now. We go 2m plus n plus L. So this in principle goes to infinity, but this condition has to be fulfilled, right? Into the time derivative of the mth time derivative of t and of mth time derivative and x derivative and y derivative, and here we still have m a plus n bar q b plus L 1 minus 1 by the power of n plus L plus m minus omega by the power of q is n is a plus n plus and b plus L and 1 plus minus 1 n plus L plus m. So, okay, this still looks, it runs to infinity, but I have to make this statement here, though, that when we have Q and this guy is 0 for all Q smaller than 0, yeah? So there's no negative terms, okay? Right, and because there are no negative terms, so maybe we could write this in a little bit more elegant fashion, but because there are no negative terms, this sum over there is finite, right? Because there's the condition that Q is equal to P minus 2 M minus N minus L, yeah? And this makes it finite, anyway. Agree? Don't agree. I mean, as long as P is finite, right? Okay, now we go, from now on we go into overtime, but you're my captives now. Right, so when we start from this equation, so this is now our master equation, and it's really amazing that I didn't write down this master equation here. So suppose now we take P equal to 0, which means we take epsilon to the power of 0, right? And evaluate this equation here. The only thing that is left for Q being, P minus 2M minus N and L, so because we start from such a low order, the only thing that will not disappear immediately is minus omega AB to the 0 order, and this is equal to 0 because the entire equation is equal to 0. So that's the only thing that's left, and it already tells us something, namely that the collision operator to order 0 is 0. Yeah? Okay, so let's take P equal to 1, which means we are talking about epsilon to the power of 1, and fill out our master equation. So what comes out now is we get a first derivative, dx of m a plus 1 b by the power of 0 plus dy m a b plus 1 to the power of 0, not to the power, sorry, to the order of 0, minus collision operator AB first order. Okay, so brackets, this is not power, I just misspoke. Yeah, so it's the order, this brackets means it's the order 0 here in the expansion. So what does this mean? Here we have something to order 0, at the order 0. So it's something that does not change with the resolution. So it does not change with the resolution. This means it does not change at all. It's a constant. So this is also constant. So if these guys are constant and you take a derivative, they of course disappear. And therefore what we can now say is that omega A B first order is equal to 0. Yeah? Because they also disappear. So the first two just disappear. So what's your question?
I mean, I don't see the P in the master equation.
The P in the master equation is here.
Yes, but how? That's not obvious to me how when P equals to 0 we got only the omega term.
Okay, let's. Now you're more captive of me. Okay, but anyway, so we put 0 into P, yeah, and then we try to count up M and N and L. Since we compute Q by subtracting 2M and N and L from P, right? This would always be negative unless M and N and L are all 0. And we know, so by the expansion that we had, the expansion of the asymptotic expansion of our dependent variables, which are the moments in the collision operator, they start from 0. So they have no negative part. Yeah? So this means whenever Q is negative, it would disappear. So, and whenever we take a derivative here, it would count up either M or N or L. And so the moments back then would go negative. So the only part that is going to remain is these guys are being all 0. Yeah, if these guys are being all 0, this here is becoming 1. Then this is 1 plus 1, yeah, which disappears with the 1/2, and we are left with omega AB by the order 0. This here, if the only part that is 0 is if they are all 0, then it's 1 minus 1, right? And they disappear, and the other ones do not exist. Okay? Thank you for the question. It's now clear. Okay, so the next P equal to 2, meaning we are looking at epsilon by the power of 2. Yeah, so now in the first, okay, when we had the first one, we could subtract 1 for N and L. Yeah, this is why we didn't have any time derivative, because whenever we have a time derivative, it counts with M, and then we have to subtract 2. Yeah, and then we are again in the negative part. Now, Now we start with 2, p equal to 2, so we can subtract m equal to 1. Right? So now we get a time derivative in this, and this time derivative, delta t m a b, now of the order 0, of course, yeah, plus dy m a b plus 1. So because we subtract one guy less here in the spatial. Okay, I've written the y term first. Doesn't matter. So here we subtract one less, so it is the first order, right? Plus dx m a plus n plus a plus 1 and b, and this first order, and the omega, minus omega, to which order comes omega? How 0? How 1? You don't know. Okay, I still have to slow down, even though we are over time. Okay, so how do we get to this term? Okay, so we started with p. If we go back to our master equation, we started with p equal to 2. Yeah. So the time derivative for every time derivative is counted up with m. So for every time derivative, we subtract 2 from q, which means we get the 0 order in the time derivative of m. Now for every spatial derivative, we subtract only 1. So we get the first order of the spatial derivative of m. Now if we don't have any derivative, yeah, so in the 0 part, the 0 part is here in the collision operator. If we don't have any derivatives, then m and n and l are all 0. Then q is equal to p. And then, yeah, so then it's 2, right? So it's 2. So, and all of this is still equal to 0. Now things are starting to be getting interesting. The first thing is, so this again, 0 order, this is constant, so it will disappear. Yeah, so the derivative of a constant will still disappear. And now we do the last one. The last one, which is of general interest, is p equal to 3, which means epsilon to the power of 3. And this gives us the time derivative of MAB. So now we subtract 2. Yeah, we subtract 2. Then we get first order, right? Plus dx, we subtract 1, a plus 1. So we count up with the derivative 1. So the indices are counted up according to the derivatives. This is very useful. And we subtract 1 from the order, we end up with order 2. We get dy m a. We count up the index b, and this is of order 2, and we subtract the collision operator ab at this. So there's no derivative, so we have now order 3. And all of this still equal to 0. So do you believe that this leads us to the Navier-Stokes equation? You have a question? Okay. Then we are now starting to be more specific. Yeah? Say we start now epsilon to the power 2 and a equal to 0 and b equal to 0. What would this mean? So this would be dt m00 of 0, where we already determined that this is equal to 0 because it would be constant, yeah? Plus dx m10 order 1 plus dy M01 order 1 minus omega 00 order 2 is equal to 0. Now we are more specific. M00 is the mass moment. The mass moment in our specific numerical method is a conserved quantity. So if it's a conserved quantity, pre and post collision are the same, and this means that omega is 0, right? This guy here. So this, because this is conserved, yeah? So specifically here. Now we identify these moments. We could just keep these names, but we like to identify them with some quantities, namely with the 0 order of the density, which is a constant, and the moment M10, we had this in previous lectures, now just in the expansion. This is the velocity. Now, but we have to take into consideration that we have to distribute this order 1, right? Because it would be rho, I mean, it's not the velocity, it's the momentum. So it's rho times u, and now rho times u could be rho 0 times ux1 plus rho 1 ux0, okay? And now we make it a little bit shorter. We know that this guy is 0 because it does not belong here, so we'll ignore this. The same M101 is of course the same thing, rho 0 uy1 plus rho 1 and uy0, which again, we say this is 0. And this means we get to the equation dx rho 0 ux1 plus dy rho 0 uy1. So rho 0 is a constant, so we can write this, we can put this in front and get to our first equation, which is now the first equivalent partial differential equation, which may be familiar with to you. So this is, of course, the continuity equation. Yeah, and this is derived by asymptotic analysis. What's wrong?
The indices for the moments are swapped. So 0, 1.
Okay, they are swapped. Yes, you're right. Thank you for helping. Okay, now this was the first equation. That was pretty simple. Now comes the more complicated. I hope until now everything was completely clear. Yeah. I just want to see you smile. So epsilon by the power of 3, a is 1 and b is what did I write here? B is equal to 0, so there's something wrong. Okay, let's have this. I believe this would be equation 6.6 now, because this outcome is now being interesting. So it's the third order, so we remain having the first order time derivative plus the spatial derivative we have in second order the moments, dy, so we have here m11, 2 minus m10 now to third order, and this is equal to 0. And now we have to introduce again our BGK method. BGK is of course the MAB. This is MAB plus MAB star divided by 1/2. So that's the definition that we already had. And the collision operator looks like this. MAB star after collision is the state before collision plus omega MAB equilibrium minus MAB, which is now the equation 6.7. So this is simply rewriting the collision operator, the BGK collision operator in terms of moments. So it's just linear transformation thereof. And what we already have introduced is MAB star minus MAB is what we call the collision operator. So now we have to look at this guy because this unfortunately does not depend on n bar. And we have an equation only in m bar. So we have to replace this with m bar. So meaning that the equation 6.7 is when okay, no, wait, I've forgotten to write down the transformations. MAB can be expressed in when you combine these two, then you see that MAB can be expressed as MAB bar minus omega AB half, and MAB star can be expressed in MAB bar, MAB star by MAB bar plus omega AB half. So that's the difference, and this we put into equation 6.7, ending up at MAB bar plus omega AB half is equal to MAB bar minus omega AB half, so it's just a replacement, right? Plus omega MAB equilibrium minus MAB bar plus omega AB half. Okay? Just putting everything into everything. And you see that these guys here are now disappearing, and what we are left with is MAB is equal to omega MAB equilibrium minus MAB bar, the guy that we know, and the omega AB half. And this can now be solved for MAB bar, which we know which we need for our equation, as being MAB equilibrium minus 1 over omega minus 1/2 omega AB. Yeah, so, and this is obviously, now this contains only the bar version and the omega, so that we can again identify this. And we put this, if my counting is now hopefully correct, into 6.6. So if we put this into 6.6, we end up with the following. So in the first moment here, the first moment is omega, is first moment to first order is rho to zero order ux to first order plus dx. Now we have to introduce the moments here, which is m20 equilibrium, now to second order, minus 1 over omega minus 1/2 omega to 0 to second order, plus the replacement of the m bar here is m11 equilibrium to second order minus 1 over omega minus 1/2 omega 11 to second order, and of all of this we still have omega 13 to third order, and all of this is equal to 0. So now in our method, now this is now specific to our method, but in our BGK methods we have, so this comes from a previous lecture, of course, we know that the equilibrium of the second moment is equal to theta times rho. Now this must be second order because we are talking about second order, yeah, equilibrium. Plus, what was this? Plus ux first order, so it is ux first order square. Ux first order square is of course second order, yeah, because it comes with epsilon each time, so it's epsilon square. This times rho 0. We know that M11 equilibrium to second order is ux to first order times uy to first order times rho to 0 order. So if we count up the orders, we see it's 2, right? I notice everybody here is enjoying this. Okay, now let us produce equation 6.8 then. By putting this into the previous equation, this is again the time derivative of ux1 plus dx theta rho, now second order, plus u1 square rho 0. So I'm now isolating the equilibrium part. So I write the equilibrium of y ux1 uy1 and rho 0 order, and then I take the non-equilibrium part where we have this 1 over omega minus 1/2, yeah, and we have the dx of omega to 0, second order, plus dy omega 1/1 also to second order, and what we should not forget is that we still have this omega 1/0 to third order left, and all of this is equal to 0. Yeah, yes, thank you. So, okay, so what is then still missing are these guys here. This is something which we don't know, and for this we use again our master equation. Yeah, we use our master equation by taking epsilon to the second order, so it's p because we're looking at second order. We have, we're looking at the moment 2, 0, so we're looking at a equal to 2 and b equal to 0, and then we look up what the master equation tells us. The master equation then tells us that we have the time derivative of m20 to 0 order, which we know is equal to 0, yeah, because it's a constant. Then dx m30 to first order plus dy m21 to first order minus omega to 0, 2. So actually what we are looking for is omega, right? So we just rewrite this. As omega to 0 to second order, which was we were looking for, is dx m30 bar first order plus dy m21 first order. And right, so these guys are to first order. What do we know about first order variables? So we were looking, yeah?
The derivative is constant?
No, the derivative is not, they are not, the derivative is constant. No, the derivative is not, the variables are not constant, and so their derivative is also not constant. They can, but what about the collision operator? we notice that the collision operator to order 0 is 0. And to order 1 is also 0. Right? Collision operator to order 1 is 0. When the collision operator to order 1 is 0, then the first order moment, not the first order moment, any moment to first order will be equal to its, the pre-collision and post-collision would be equal. Yeah? Because they don't change in collision. And they only don't change in collision in a BGK operator if they are equal to their equilibrium. Right? So this is why we can write that this is dxm30 equilibrium first order plus dy m21 equilibrium first order. Yeah? Because their collision operator is 0, and this can only be when they are the same as their equilibrium. Okay, so this. Excuse me?
What is the moment 30 in terms of rho and u?
Yeah, okay, let me just write this down, otherwise I forget. Omega AB to first order is 0. This is the reason. Now, what we have here? So what is M? So the question was, what is M equilibrium first order equal to M? So this is, as we introduced, this is an alien. Yeah, so there's aliasing in it. So it's M0, this is M30 is equal to M10, equilibrium first order, which is, of course, rho 0 order ux first order. Yeah, and equally we have M12 equilibrium first order is equal to theta ux first order, and M21 equilibrium first order is equal to theta uy first order. Yeah, so this comes from the equilibrium, and all of this we can now put into equation 6.8. I still have one. 6.8, and then we get to the equation everything is equal to 0. We have the time derivative rho 0 ux 1 plus dx theta rho second order plus ux first square rho 0 order. So these are the equilibrium parts, the y ux first order, uy first order, rho 0 order. We have minus 1 over omega minus 1/2, and what I'm doing here now, so we had the first derivative of this collision operators, which again include a first derivative. So now we get to second derivatives, and now I take the freedom to already arrange them in a convenient way. Yeah, by saying I first take the second derivative in x only, and because this comes from this third moment here, yeah, what we have here is just ux first order rho 0, and now I take here the yy, which comes with theta ux first order rho 0 order, because this originates from this moment here. So there's a theta in front of this, plus we have mixed terms. The mixed term appears twice. The mixed term comes actually from this moment, and it appears twice, is u y first order theta rho 0 order. So, and not forget omega 1 0 to third order. Now, what we are going to do is we are looking specifically at this part here. We're taking this out and I call this A. And I again rewrite this a little bit as A equal to rho 0 theta. So these are constant. They are taken out. Ux first order plus dyy ux first order. I'm taking these guys out because I know already the Navier-Stokes equation, and I know that these guys here appear in the Navier-Stokes equation. So I isolated them, right? So then what I'm left with is the guys that do not appear in the incompressible Navier-Stokes equation. And these are dx, ux first order. So what I've done here, okay, I should have the brackets here. What I've done here is I've taken the second derivative of ux with theta. Yeah, if you look at the equation above, there was no theta here, right? So I artificially introduced a theta there. So I have to repair this by taking 1 minus theta in this part, dxx, yeah, ux. So this is now the same thing summing up in the right way, plus dy 2u y first order theta rho 0 order, which is the guy back here, okay? And closing all the brackets. And now we call whatever is in this bracket, we now call this B. So B is the thing that does not appear in the Navier-Stokes equation, which means that B is supposed to be 0. Yeah? And what now helps us is what we see. We have a dx ux and a dy uy. And we know from the previous equation that we derived this, the divergence of u to first order is equal to 0. And now that would help us if these prefactors that appear in the equation, which is 1 minus theta on one side and 2 on the other side, if they would be the same. So if we have 1 minus theta being equal to 2 theta, then B will disappear, right? So, and this is the case if theta is, as we already derived in a different way, if this is equal to 1/3. So finally, with half an hour overtime, okay, but you know, the important thing is that we arrive, not when we arrive, right? So finally, we have we can arrange this as the time derivative of ux first order plus dx ux first order square rho 0 plus dy ux first order uy first order rho 0. So, and this, all of this together is what we call a material derivative. So this is what usually is seen in the Navier-Stokes equation on the left-hand side. So I bring the other things therefore on the right to the right-hand side, and we have dx theta rho square. Now we identify this as the pressure. We just call this the pressure, minus theta rho 0, 1 over omega minus 1/2. This, there must be a plus plus. This is the viscosity. This is the viscosity, and this goes into dx x u1 plus dy y ux ux1. So this, yeah, right. So this is of course Laplace ux of first order, obviously. And then there is the thing we've always carried on is this omega 1, 0. So what is this? So this here is the body force. Or the, no, okay, we should not, let me see, we write it, yeah, it's the body force. So yeah, it's the, it could, for example, be the acceleration, and all of this together is the Navier-Stokes equation, which we now, the Navier-Stokes equation in X, which we now derived. So thank you for listening. I will now end the stream, and I will now end